Every time you send an email or buy something online, or even just browse the web, there's this invisible architecture working in the background, keeping all your information safe. That's the world of cryptography, the hidden science of keeping secrets. So let's pull back the curtain and see how this whole thing actually works.
Now, you might think securing information is, a modern problem, but people have been wrestling with this for ages. Even this 19th century military guy, Clausewitz, knew that all the different factors make it, as he said, a fairly complicated matter. Long before computers were even a dream, we had this fundamental challenge: how do you communicate securely? So, what are we actually trying to do here? Well, in information security, the goal is always to hit these three targets. It's called the CIA triad. First, confidentiality. Pretty simple, only the right people get to see the data. Next, integrity. You need to be sure the data hasn't been messed with. And finally, availability. You gotta be able to get to your data when you need it. This triad, it's the bedrock of everything we're about to get into.
Okay, so with those goals in mind, let's zoom in on the core problem cryptography was built to solve in our modern digital world.
Here's the classic setup. You've got user A, we'll call her Alice, and she wants to send a sensitive file to user B. Let's call him Bob. But lurking on the network is user C, Eve, the eavesdropper. Now, if Alice just sends the file as is, Eve can just grab a copy. So the huge question is, how do we make that file completely useless to her?
The first major solution to this puzzle is an idea that's actually been around for centuries, just supercharged for the digital age. And it's all built around one single, shared secret. It's called Symmetric Encryption. And the idea is just brilliantly simple. Alice and Bob agree on one secret key, just one. Alice uses that key to scramble or encrypt her message. Bob then uses that exact same key to unscramble or decrypt it. It's symmetric because the same key works both ways. A really old-school example that shows this perfectly is the Caesar cipher. Here, the key isn't some complex file. It's just a number, in this case, 3. You take your original message, the plain text, and you just shift every letter forward 3 spots in the alphabet. So M becomes P, E becomes H, you get the idea. The result is ciphertext, and it's total gibberish unless you know the secret is shift by 3. And this right here, this is the core principle of all modern cryptography. It doesn't matter if everyone knows how the Caesar cipher works. The method, the algorithm, that's public knowledge. The only thing that matters is keeping the key, the number 3, a secret. If Eve gets the key, the whole system just falls apart. Okay, so that leads to a really critical question. With today's computers, Eve doesn't have to be some genius code breaker. She can just try every single possible key until one works. That's called a brute force attack. So how long does our key need to be to make that basically impossible? Just look at this table. The power of key length is mind-blowing. See that top row for DES? That's an older standard. With its 56-bit key, a powerful machine could crack it in maybe 10 hours. But now, jump down to AES, a modern standard with a 128-bit key. The number of possible keys is 3.4 with 38 zeros after it. Even with a supercomputer trying 1 million keys a microsecond, it would take 5.4 quintillion years. That's longer than the age of the universe. That is computationally secure. So awesome, problem solved, right? Just use really long keys and we're all good. Well, not so fast. We've definitely solved the brute force problem, but there's a much bigger, more fundamental flaw with this whole one shared secret key idea.
And here it is, the million-dollar question. It's called the key distribution problem. If Alice and Bob are on opposite sides of the planet, how in the world does Alice get that secret key to Bob securely? She can't just email it to him, remember? Eve is listening. Sending the key is the very problem we were trying to solve to begin with. It's a total catch-22.
Solving that seemingly impossible riddle? It required a complete revolution in how we think about keys. It was a total paradigm shift. Welcome to the public key revolution.
This whole revolution is built on this really beautiful mathematical idea called a trapdoor one-way function. Okay, think of it like this. Mixing 2 colors of paint together is super easy, but trying to unmix them back into their original colors, practically impossible. That's a one-way function. A trapdoor function is the same idea, but with a secret trick, the trapdoor, that makes going backward easy only if you know the secret.
This new method is called asymmetric encryption, and it's a completely different beast. Instead of one shared key, now everyone gets a pair of keys that are mathematically linked. One is your public key. You can post it on a billboard, you don't care who sees it. The other is your private key, and you guard that with your life. This idea didn't just solve the key distribution problem, it basically made the entire modern secure internet possible.
So how does this magic work? It's genius. Think of Bob's public key as an open padlock. He can make copies of this open padlock and give them to anyone, including Alice. So Alice writes her secret message, puts it in a box, and snaps Bob's public padlock on it. She sends the locked box over the internet. Now here's the magic trick. The only key in the entire universe that can open that padlock is Bob's private key. Eve can grab the box, but it's just a locked box to her. She can't open it. Problem solved.
So asymmetric is the clear winner, right? We should just use that for everything? Well, remember that comparison chart? It's a lot slower. It takes a lot more computing power. So the real-world solution, the one that's happening on your computer right now, is to cleverly combine both of these ideas to get the best of both worlds.
This is exactly what happens every single time you see that little lock icon in your browser's address bar. Your browser and the web server use that slow but super secure asymmetric encryption for one job and one job only: to securely create and share a brand new throwaway symmetric key for this one session. Once they've both got that shared secret, they switch gears and use the lightning-fast symmetric encryption for all the actual data: the text, the images, everything. It all boils down to this really simple phrase: asymmetric for the handshake, symmetric for the data. This hybrid approach gives us that unbreakable security of public keys for the setup and the blazing speed of symmetric keys for the actual conversation. It's the perfect combo. And these concepts, they aren't just for textbooks. They are the invisible foundation of pretty much our entire digital lives, working 24/7 to protect us.
So what does that protection look like in just raw numbers? It looks like this. 2 to the power of 128. That's the number of possible keys for the modern AES standard we talked about. It's a number so outrageously huge that our brains can't even really comprehend it. And that number is what's standing between your private data and the rest of the world.
And this really gets to the heart of it all. Security isn't a problem you just solve once and then you're done. It is a constant, non-stop battle of wits. Attackers are always looking for new holes, and defenders are always trying to patch them and build stronger walls. It is a perpetual arms race. And that brings us right to our final thought. As new technologies like quantum computing start to become a reality, they actually threaten to break the very trapdoor math that our public key systems rely on. This battle of wits is far from over, which means the quest for keeping secrets safe never truly ends. And it leaves us with a huge question: what will the next cryptographic revolution look like?